Hello, so welcome back again. And as we are interested in this problem statement today, and the problem statement is in the circuit shown below, all the components are said to be ideal. And if the input voltage is 2 volt, so right here you got this input voltage which is said to be 2 volt. The current I naught sourced by the op amp is dash milliampere. So basically we have to understand what will be the current I naught that is sourced by the op amp if you apply input of 2 volts. So here is clearly an amplifier with a gain A. You got the resistors and you got the load resistance also. So if you closely inspect the circuit, of course, you have plus minus 5 volt supply voltages. So if you closely inspect the circuit, you see that we have negative and the positive input of the amplifier, which is differential amplifier. Input is applied to the positive pin. To the negative pin, you got the signal coming from the output side by means of a feedback via this resistor, and also to the negative pin you have one resistor connected as shown, and then the op amp supplies the output current I naught, and it will also have the output voltage V naught. Okay, but the question we have to answer, what will be the value of I naught? So obviously, if you closely see this, this is a non-inverting amplifier actually, non-inverting amplifier. Why? Because your input is applied to the positive pin of the amplifier, which is a non-inverting pin, assuming the gain of the amplifier is A naught L, which is open loop gain. And you got the feedback configuration where the feedback is provided to the negative input pin from the output side. So as we can know already, the output voltage, which is the here, is basically the, in the case of non-inverting amplifier, it can be written as 1 plus RF over R1 multiplied by VI. So here is your VI. RF would be this value of the resistor, which is the feedback resistance, and R1 would be this resistor. Now, how we get this expression is by applying the, by using the virtual ground concept at this node, and assuming that the open loop gain AOL is very, very high, and we have, and then apply the KCL at this node, Kirchhoff's current law, and you get to know this expression of the output voltage. So if you want to know how we derive it, we have that done that in other modules, so you are encouraged to refer to that. But currently we are just focusing how to find the value of I naught. So obviously you, excuse excuse me, you don't know the value of the gain here, but you know the value of the resistor. So obviously we can say that output voltage will be 1 plus resistor RF is 1k, R1 is 1k each, and the input is 2 volts. So if you solve this, this goes about 1 plus 1 multiplied by 2, that is 2 times 2 is equal to 4 volts. So your output voltage is 4 volt. So how to get the value of I naught? We want to know the value of I naught actually. Okay. So at this node, we can see that you have one branch of current, one current that is flowing in this direction, going back to the negative pin, and one part of the current is coming to flow through this load resistance of 1k, and there is this current that is entering into the node. So at node VO, we would say apply KCL, that is Kirchhoff's current law, at the node output node, that is VO, and we see that there is this current, let's call it IL, and then there is this current, let's call it as IF, because it is flowing in the feedback path. So we see I naught would be, which is the incoming current to this node, will be equated to the outgoing current, that will be, let's say, IL plus IF. What is IL? It would be V naught divided by the value of this resistor 1K, and plus IF would be VO, that is the voltage difference across this resistance RF, okay, divided by the value of the resistor RF itself. V naught minus uh, this voltage, the voltage at this node. Now, what is the voltage at this node? Assuming that AOL is very high, so we know that AOL is basically the difference between V1 minus V2, which is V1 minus V2 is VID, and this is the differential voltage. Okay, so if we say that V1 minus V2 would be output voltage divided by the gain. So if the gain is very high, that means in ideal case, we actually assume that the gain is infinite. So output divided by very high value of a gain. So this VID actually gets negligible. So difference will be very, very low if the gain is very, very high, okay, and vice versa. So if this, in a case of ideal, we said that all components are ideal. So op-amp is ideal. It means the gain is AOL tends to infinity, then VID tends to 0. It means V1 minus V2 tends to 0. That means V1 comes at the equal potential, or V2 comes at the equal potential as at the other potential. V1 equals to V2. So you got the, let's say, this is the voltage V1 and this is the voltage V2. So assuming that the AOL is infinite, so V1 and V2 are at the same potential. So we say that V naught minus, let's say, this is VI basically, and V1 is actually VI you are here. So VI is 2 volt divided by the value of the feedback resistance, that is this one. So I hope you got the concept how we are saying that this is a VI. Okay, VI is nothing but what is the voltage you apply to the positive pin. And due to the assumption AOL is extremely high, these two potential are at the same voltage. These two nodes are at the same potential. So this virtually the voltage at this node comes at this node. So 2 volt at the same level. So solving this, you have voltage VO is equal to 4 volt divided by 1K plus VO minus 2 volt. So obviously again I will write here, well, this is 4 volt minus 2 volt divided by 1K, right? So solving this, 4 by 1 plus 2 by 1, that is actually 4 plus 2 is equal to 6 volts. So you got the 6 volts, no, this is the 6 ampere actually. So I naught, value of the I naught is actually 6 ampere, milliampere actually, because these are 1K each, okay? So 6 milliampere is the output current. That's the answer. Okay, so hope you found this video useful. If you did so, you can share it with others for a wider reach. Stay tuned for more engaging contents like this. Subscribe to our channel. Till then, wish you happy learning.